So the next couple of situations that I want you to think about involve cars turning corners, basically. And these are kind of neat because it gives us examples that show how both the force of friction and the normal force can be responsible for centripetal acceleration. So the first thing that I want you to think about is basically this situation. So we imagine a car that's going around a corner. And you can imagine this, as a road that has some radius. The turn has some radius r here. And basically, in this situation, it's the force of static friction that's providing AR. So what we can do is let's sum the forces in both y and r. So we can think of this coordinate system as basically r and y. And if we look at the forces in y, we have our familiar normal force and force of gravity. And those are going to equal 0 because it's not accelerating in y. So this tells us what the normal force is. And then if we look at the sum of the forces in r, what are we going to have? We'll have the force of friction, force of static friction. That's going to equal the mass times acceleration in the radial direction. But we know that that's equal to v squared over r. So we have a relationship between friction and the centripetal acceleration. And we also know that the force of static friction is equal to mu s times the normal force. And we found the normal force from looking at the forces in y. So we can see that this is going to be mu s mg equals mv squared over r. Notice the mass appears on both sides. And so now we have a relationship between the coefficient of static friction and the velocity and the radius of the curve. So in this situation, it's friction which is providing the ability to turn the corner. So this is in contrast to the situation that you're, I'm sure, familiar with from driving on the highway, especially situations where you're at high speed, and that's the following. So when you're at high speed, you'll notice that curves are banked. They're curved rather than flat. And what this allows for is that a component of the normal force is directed towards the center of the circle. So think of this as, this is a circle as well. Some radius here. And that component can provide centripetal acceleration. So let's look at this just like we did with the flat curve, where we sum the forces in y and r. So if we look at the sum of the forces in y, we'll have the vertical part of the normal force minus the force of gravity on the car, and that's going to equal 0 because it's not accelerating in y. But this gives us an expression for the normal force that we'll be able to make use of. And then if we look in the r direction, so towards the center of the circle, we have the component of the normal force that's pointed inward. And we know that that's going to equal the mass times the centripetal acceleration. And, we know, of course, that this is mv squared over r. So we can substitute this thing in for the normal force. Oh, wait a second. Sorry, this is sine theta, our r component. And notice it doesn't depend on the mass. That appears on both sides. And we can consolidate this a little bit, dividing our sine theta by cosine theta. And this gives us a nice, and dividing through by g. We have a nice expression that relates the banking angle to the velocity of the car around the curve and the radius of the curve. And the thing that's cool about this is this isn't making use of friction at all. So this is centripetal acceleration provided just by the banking angle. So we could incorporate friction into this picture as well, but it gets kind of complicated. So for now, we're just going to assume there isn't any friction. So this is how curves are designed for high-speed travel. And I'm sure you've encountered this, on the interstate. So let's look at an example problem that makes use of some of these ideas. So let me paste one in here for you. So here's a question. How large must the coefficient of static friction be between the tires and the road if a car is to round a level curve of radius 85 meters at a speed of 95 kilometers per hour? And what banking angle would allow the same centripetal acceleration without the presence of any friction? Okay, so let's give ourselves a picture here to try and understand what's going on. So we have some curve that's 85 meters in radius. And I have a little cartoon of our car here. Okay, so, and this thing is going at a velocity of 95 kilometers per hour. And of course, centripetal acceleration is pointed in. And the force of friction is pointed in as well. And that's what's providing our centripetal acceleration in this flat curve scenario. So we have an idea of the forces, what's going on. It can be helpful to have sort of the back view with this situation as well. So we have our car. It's at some radius r. There's a normal force that's pointing up. There's our force of gravity pointing down. And then the force of friction is pointing in. Okay. So, and let's look at the sum of the forces in R. We're going to have the force of friction, and that's going to equal the mass times the centripetal acceleration, which we know is v squared over r. Now, the force of friction, we know that that's going to equal, since this is a flat curve, remember generally the force of friction is mu times the normal force, mu s in this case because it's static friction. The normal force is just going to be mg because this curve is flat. It'll be equal to the force of gravity. We can stick that in here. Okay, so the mass will drop out. We can solve this then for the coefficient of static friction. The coefficient is going to be equal to v squared over rg. And then we have some numbers to work with. So what do we have? 95 kilometers per hour. So let's put this in meters per second. So kilometers, 1,000 meters per kilometer. 1 hour, 3,600 seconds. And notice that's squared. And the radius, 85, 9.8 for g. Compute this, we find that the coefficient of static friction that would allow us to turn this corner is 0.84. Okay, which is reasonable for tires on a roadway. Remember, tires are pretty tacky, so we expect a pretty relatively large coefficient of friction. So this seems possible, reasonable. And then the second part of the question, what banking angle would allow the same centripetal acceleration without the presence of any friction? So recall here, the relationship that we were using was that the tangent of the banking angle is equal to v squared over gr. Notice this quantity v squared over gr is the same thing as the coefficient of static friction. So in other words, tangent theta is equal to mu s, what we have for mu s, so we can just take the inverse tangent of rv squared over rg, and that's 0.84. And when we do that, we find that theta would equal 40 degrees. So this would be the banking angle that would provide the same effective centripetal acceleration. So this is kind of a nice combination of examples that show you how both friction and the normal force can provide centripetal acceleration, allowing, in this case, a car to turn a corner.